Hi. So well done for staying with me. So if you recall, I filled in the detail from the last part, looking at the stress tensor, the boundary stress tensor for 4 dimensions, which is constructed from this data T mu nu in this Pfefferman-Graham expansion here, and also the boundary metric and the second term in this Pfefferman-Graham expansion is G2, in the following way. So I won't dwell on this. You can pause your video and work it out. Kostas Skenderis has some nice lecture notes on this. They're called, they're from around 2000, and they're called lecture notes on holographic renormalization. So you can get more details there. But in particular, this term G2 is actually constructed from the boundary metric like this in 4 dimensions. So the point is that if you want to compute the boundary stress tensor, you have to extract this from the expansion. You know what the boundary metric is. You compute this. You compute all of these terms and subtract them from there in order to get the actual boundary stress tensor. Something I should have said is that the boundary stress tensor, T mu nu, is then in the gravity is equal to the expectation value of the stress tensor operator in the CFT. So in AdS-CFT, calculating this really is calculating the expectation value of the stress tensor in the CFT in whatever state the CFT corresponds to that bulk geometry and the gravity. So if you're in AdS vacuum, like the Poincare vacuum, you're just got a flat boundary metric. You should have a vanishing stress tensor. You calculate that in question 1. And that's telling you in the vacuum, in flat space, the CFT has vanishing 1-point function of the stress tensor. But if you're in a black hole state, if you're at finite temperature in the CFT, there may be a black hole bulk dual with some Hawking temperature, which is the temperature of the CFT, and then this thing won't vanish, and indeed this thing won't vanish. And when you compute this for your black hole, as you do in some of the questions, you will be computing the 1-point function in some thermal state of the CFT, which is pretty remarkable thing to be able to compute, given that these CFTs are strongly coupled. As I say, I don't want to dwell on the CFT aspects of all of this. I'm really going to focus on gravity here. And I'm just going to quickly review what I might call Euclidean methods to find the temperatures of black holes, and what a nice geometric way to think about black hole solutions that really works for static black holes. And so you may have seen this. If you've seen this, you can skip this bit, but if you haven't seen it, do take a look, and certainly in the problem sheets, get some practice using these methods. They're very beautiful, and they date back to the 70s with work of Hawking, Gibbons, many others in Cambridge and elsewhere. So for static geometries, and it doesn't really work so nicely if you've got stationary black holes, but for static geometries, we take t goes to I tau, Euclidean time, and then our Lorentzian geometry goes to Riemannian or Euclidean geometry. And we want it to go in particular to a smooth Euclidean Riemannian geometry, meaning there's no time, your signature is just plus, 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 plus. So for example, we've got flat space. If we've got flat space, so we'll forget about AdS here, but you can practice it in the AdS examples in our in the problem sheets. We go to flat Lorentzian space-time. Minkowski goes to just flat Euclidean space-time. If we take tau and identify it, Euclidean time, identify it with some period, we wrap it up into an angle, which we can certainly do here. It's a global thing. Then that's equivalent to putting fields living in the geometry are put at finite temperature. T is 1 over beta. So beta, if you've ever done thermal field theory, if you want to calculate thermal quantum field theory, the very nice way to think about it is to think about field theory living in the Euclidean space-time with periodic time, where the inverse, or the period of the time inverted gives you the temperature. And it's a sort of neat trick in quantum field theory to compute equilibrium thermal physics, but it works beautifully. And the key point is that it really still works in gravity. That was the remarkable observation of Hawking, Gibbons, and others. So let's see how this works for a black hole. So for, if we do it here for flat space, all we're doing is putting flat space at finite temperature. It doesn't really, we don't learn anything. We can certainly say that's compact. If we do quantum field theory in this Euclidean quantum field theory in this space, we'll recreate thermal quantum field theory, but from the point of view of the geometry, it's rather trivial. But let's think about a black hole. Let's take Schwarzschild. Let's do another example. Schwarzschild, and this is just asymptotically flat Schwarzschild, but you can do this with the AdS versions in the problem sheets. So if we've got asymptotically flat Schwarzschild, well, here we go. Here's asymptotically flat Schwarzschild, as we all know and love. And we can continue this. Let me just do it here. When I continue this to Euclidean time, I get this metric here. Now note, it's still real. That's the key point, and it's real because it's static, and I don't have any. If I had sort of dt, d theta terms or d phi terms, so a rotating black hole, this wouldn't work, or it's much more subtle. But this is certainly still a real metric, and we can try. Let's take tau goes to tau plus beta. Okay. Now, if we take a tau plus beta, the point is, in the Euclidean methods, we want the geometry to be smooth. Now, here, it turns out that if you don't do this, this geometry is not smooth at what would have been the horizon, r equals r naught. But we can make it smooth by compactifying tau with exactly the right period, and there's only one period that'll do that. What is that period? Well, it's the inverse Hawking temperature. So this is a very beautiful way to calculate the Hawking temperature of a black hole. This is a very beautiful way to think about it. So it tallies exactly with what we would do in quantum field theory when we think about finite temperature. To say it another way, fields in this background with this identified will feel as if they're at finite temperature with temperature 1 over beta. So how do we do this calculation? How do we see that this is smooth for a particular beta? Let me go through it, and as I say, you can then sort of try this in the AdS examples. So we'll expand around the horizon, r is r naught, by changing coordinates in this way. So we change to r naught plus mu squared. And that works when you've got metrics that go like sort of f and 1 over f here. More generally, we basically want to go to a coordinate which makes this whole thing a sort of nice proper distance coordinate. This r is not a good coordinate because this blows up, but we could certainly change this. We might change this to some new coordinate. Let's call it d rho squared, where that whole thing, we just go to normal coordinates to the horizon. But pragmatically, we can do for this form of the metric, we can try this. And then 1 minus r naught over r is 1 minus 1 over 1 plus, if I haven't got all this wrong, like this. And that basically, expanding around mu is 0, which is the horizon, gives me this. dr is 2 mu d mu. And so using all of that, then the metric becomes near mu is 0. I get this for the d tau squared term. I get, note the mu squareds here cancel. I get this term here, so that cancels that. And I also have my the horizon and corrections in mu as I go away from mu is 0. So here is the horizon, the S2, And what we can see if we just slightly rewrite this, if I pull the factors together, I can write this like this. So what we see is locally, we have an S2, and this really is a disk, a 2-disk. Or rather, more precisely, tau, if tau is compactified correctly, this is like a 2D plane. In fact, it's not really a disk. Sorry, I shouldn't call it a disk. Maybe I should say it is sort of a disk. But let's say it's basically like R2, where this mu is 0, let's say R2 in polar coordinates. And mu equals 0 is like the origin. Okay, so the horizon is like an origin, and you have a symmetry generated by d tau, which is the polar symmetry in this R2. Now, for this to be smooth and not have a conical singularity, you need this period here to be exactly the right one, so that as I go round in tau, all the way round from tau is 0 to tau is beta, I've gone round 2 pi. Otherwise, we know we'll have a conical deficit. So we can see here that for regularity, to have a smooth and not a cone, we need 2 pi squared to be equal to beta squared over 4r0 squared. Okay, that, as I say again, going round here from beta is 0 to sort of integrating the proper distance round here, well, integrating the period round here, I should say, should give me 2 pi squared. Okay, and I get that factor, and I also get beta squared from the tau, and that tells me that beta is 4 pi r0, which tells me that T is 1 over 4 pi r0, and this is the Hawking temperature. And so we've just calculated, just from smoothness of the geometry near the horizon, we've calculated the Hawking temperature. And this agrees with Lorentzian calculations, but it's a very beautiful and sort of elegant way to think about it. And pictorially, we can think of the black hole as looking like this. In Euclidean, tau sort of generates a rotational isometry, and at every point here, we've got a 2-sphere, including at the horizon. So this is the 2-sphere here of the geometry. Near the horizon, it's just got a constant size, but it gets bigger and bigger and bigger as you go out in R. And this is R equals R0 at the horizon. And the horizon really becomes what we call the tip of the cigar. Okay, so it's like a tip of the cigar. This is how we think about Euclidean black holes. Okay, so everything is nice and smooth here. It's just the geometry closes smoothly provided you're at the right temperature. It's a very beautiful method for calculating things. Just a comment on that. In AdS, when we make this identification, when we go to Euclidean time, it of course changes the boundary metric to also be Euclidean. So we could think in the Poincaré setting, this might be the boundary metric of our Poincaré AdS or asymptotic Poincaré AdS space. When we do this continuation in the bulk, it also Euclideanizes the boundary. And when we make this identification, it also makes the boundary have periodic Euclidean time. So our CFT is now living on a Euclidean space at finite temperature with a periodic Euclidean time. So this Hawking temperature, say I've got a black hole in the bulk with this temperature here, matches the temperature of the boundary CFT. They're both at the same temperature. Okay, just something to note, just a comment, it's a slightly fiddly comment, but in one of the problems that might be useful. if I have a space-time which in Euclidean signature looks like this, and I compute the boundary stress tensor in Euclidean signature, just something to be aware of is that rather than in Lorentzian, where using my conventions, the time-time component of the stress tensor would be the energy density, when you flip to Euclidean, you actually get a minus sign there. So it's just something to slightly be aware of. Okay, great. So using those techniques in the problems, you'll calculate the temperature of various black holes, and you can calculate the area of the horizons and the entropy using the usual Bekenstein formula. You can also compute the energy of the black holes using the boundary stress tensor to get the energy density and integrating it up. You can do all of that. Let me tell you some of the results. In the planar case, AdS black holes, AdS Schwarzschild, the first thing to note is that the specific heat is positive. And so these are already black holes that can have an infinite horizon area, Euclidean space. We can compactify everything onto a torus so that the boundary becomes a torus and the horizon becomes a torus, make it finite, but we don't have to. But the interesting thing is the specific heat, unlike asymptotically flat Schwarzschild black holes, which have negative specific heat, the specific heat of AdS planar black holes is positive. It's very important because these black holes have a temperature and they represent the thermal states of a dual CFT. Now, if this CFT has any sensible thermodynamics, it had better have positive specific heat, because otherwise it's a sort of sick theory in the old sense of the word sick, not the modern one. And so really, the fact that black holes can have positive specific heat in AdS spaces is very important for the whole consistency of this picture. So it's not a sort of trivial fact. The global AdS black holes are even more interesting. So these ones I wrote down before, remember they had a parameter R0 in. You might have to go back and look at your notes on that. But if you calculate the temperature as you will in the questions, I think you should deduce the temperature goes like this. This is not, this is D, not dr, it's not differential, it's dimension times R0 squared plus D minus 2 L squared. So there's a really interesting behavior. In this planar AdS case, really the only scale is the temperature. I mean, basically the temperature I think was 1 over 4 pi Z0. Okay, so it's very simple. And the physics is sort of very simple because there's no other scales in the problem. Whereas if in this case you've got a sphere and you've got the radius of the sphere, here the boundary is time cross a sphere. And in some sense, a sphere, we can think of the sphere as having unit radius or radius L, it depends on the frame you're in. But the point is there's some radius of the sphere. And so when you put your field theory at finite temperature, there's a more interesting physics because you've got both the temperature of the theory, the size of the Euclidean time circle, but also the size of the sphere it's on. And you can have some interesting physics as you change the ratio, and that gives you this more interesting bulk physics. And if I plot T against R0, you find that actually there's a minimum temperature for these black holes. And if you do the calculations in the problem sheets, hopefully you can see that this minimum temperature is related to the AdS scale by some factor depending on dimension. You'll also see from here, you will also compute the free energy, which if I remind you is E minus Ts. Free energy is the relevant potential, thermodynamic potential to consider when you're in the canonical ensemble, when you're working at fixed temperature. And so if we think of working at fixed temperature in the field theory or in the gravity, the question is, what is the preferred phase if there are multiple phases? Now we can always take our AdS solution, just our global AdS, and compactify time into a circle. that's perfectly fine and is just what we call thermal AdS. Now, it's got a particular free energy. In fact, its free energy will vanish in most, but not all. Well, anyway, let's just say you're in 3 boundary dimensions for bulk. Its free energy will vanish. It doesn't have any horizons. This isn't there, and the energy, it turns out, just vanishes. However, you also have these black hole solutions, and if you're at low temperatures here, there aren't any black hole solutions. The only option is this AdS space, sort of put at finite temperature. But if you are at finite temperature here above this minimum temperature, there are 2 black holes, a small one, small R0, small horizon, and a large one. So these are the large black holes, and these are the small black holes. And it turns out these have positive specific heat when you work out the energy, and these have negative specific heat. And it further turns out that if you calculate the free energy of these solutions and the free energy, well, of global AdS itself, just with its Euclidean time wrapped up, which doesn't really change things, you find that global AdS dominates at low temperatures. In fact, it's the only thing at low temperatures in this temperature regime here. There aren't any options. In fact, it still dominates over these black holes for a little higher temperature, but at some point, this phase here dominates at higher temperature. And so, in fact, it's exactly, I think, at R0 is L, where this is the dominant phase at this temperature range. So for this temperature range, these large black holes dominate. And there's a phase transition. This phase transition, if you look at F as you will in the problems, there's a phase transition from global AdS to large black holes. And this was originally studied by Hawking and Page. This is the so-called Hawking-Page phase transition. And in CFT language, is telling you that if you put a CFT on time across a sphere at finite temperature and vary the size of the thermal circle, vary the temperature, then at some scale fixed by the sphere, there will be a phase transition. And this, in fact, when the CFT is a gauge theory, is associated to what's called a large N deconfinement phase transition. You go from having a phase with confining behavior, the global AdS, to a phase with deconfined sort of plasma behavior, which is represented by the black hole. Note we have the first law. And for these black holes, the first law is very simple. And the first law is very useful. dE is TdS. It's very useful because if you compute, say, using Euclidean methods, T and S, you can figure out what E is, or at least up to a constant when you integrate this, what E is, without, for example, having to compute a boundary stress tensor. So this, you should always remember the first law whenever you're doing black hole calculations, because it can short-circuit shortcut lots of complicated calculation. It can be very clever. Very useful practically. Note, let's just consider our planar case. Again, as another example. Now remember, we have this planar AdS Schwarzschild. And here it is. This I've already written down before. This, again, has this nice temperature. In fact, sorry, I wrote the temperature wrong before. It's D over 4 pi Z0. Yeah, D over 4 pi Z0. Sorry, let me correct that. Where did I have it before? I can't even remember now. Apologies, wherever I wrote it down before was probably wrong. I'll try and, yeah. Anyway, so, oh yeah, planar black hole, there we are, D over that. So here we go. We've got this, this solution with its temperature, and remember, when we go to the Euclidean setting, we can think of this as going to Euclidean time, and then tau is periodic with period beta. Okay, now supposing we are in this toroidal setting, where we compactify the x's so that not only the bulk has been toroidally compactified, but the boundary metric is also toroidal, so it's time cross a torus. Okay. Now that's a slightly more interesting situation because, like in the global AdS case where you've got a sphere, you've got a torus of some finite size, and you can ask, as I change the temperature relative to the size of the torus, does something interesting happen? Well, it turns out it does. You can always just consider AdS in this context, like this, wrapping up, it's like thermal AdS. That's a bulk solution. We have our bulk black hole solution here. And it turns out that black hole always dominates AdS if you calculate its free energy, which you will. But there's also, in this setting, the so-called soliton. And we can see it very nicely. It's called the AdS soliton. It was discovered by Horowitz and Myers. And it's basically just a sort of, from a Euclidean point of view, it looks exactly like this black hole. We just take, instead of Euclidean time to shrink at a horizon, we take one of the this is really, let's call it tilde here, one of the spatial circles, which now is periodic with length L. So this is just one of these directions, whichever one you like, okay, to shrink. And this constant here, just as this constant here is related to the temperature and therefore to beta, this constant here is related to L in order that this geometry is smooth. So there's a smooth, what's called AdS soliton. I'd say I'm not quite sure why it's called the AdS soliton, but anyway, it is. And so you've actually got these two, and it turns out that this also dominates AdS. It doesn't have any horizon, just like AdS, or no thermal horizon. There's nothing in front of here except this conformal factor. So this, it turns out, however, has a negative energy with respect to AdS and therefore dominates in terms of free energy. And as you show in one of the questions, there's actually a phase transition. As you increase the energy, the temperature, sorry, this was the dominant phase, and then it changes to this. So actually, in this case where you have a toroidal boundary, you have a very similar behavior to the Hawking page. At low temperature, you have a solution without a horizon, the so-called AdS soliton, and at high temperature, you go over to a black hole. Okay, so there's an interesting structure there. Now let me finish this sort of lecture with a discussion of the gravitational path integral.